recording. Okay, so the next section we're covering is 22.5, and this is actually the second half, the second important thing that we want to figure out in this chapter. The first thing is basically the relationship between electric fields and voltages. You know how you do the integral to get from electric field to voltage, right? That's the relationship. Delta V is integral of E dot ds, and we'll did some practice on how to simplify that dot product buried inside an integral, right? A lot of times you don't want to deal with vector calculus and integration at the same time, right? So a lot of times I give you guys a problem where, you know, it simplifies, right? Oh, there's a negative sign I always forget. If you want to go from voltage to electric field, right, it's always going to be this negative. You know, let's say you want to figure out the electric field in the I hat direction. It's d by dx of the voltage as a function of x, right? Or if you want to figure out the electric field in the y direction, right, this will be d by dy. The voltage, you know, take the derivative as if the voltage only depends on y, and then can do that with k and stuff like that. So that's how you convert between the two things. That's the first thing we learned on this chapter. We also talked a little bit about batteries, but as I said, I just want you guys to have a conceptual idea of what a battery is. But the next, the second really important thing for us to learn and get a really good grasp on this chapter is this idea of a capacitor. Those of you who are old enough like me, anyone recognize what this is? It's from a movie, so one of you guys recognize it too. Okay, this is from this movie called Back to the Future, and they just call this thing the flux capacitor. Okay, and essentially it's just like, I think it's like 3 Christmas lights hooked up together. It's not really a capacitor, but this is just kind of something that I always, when I took this class in 2002, it's like, capacitor, isn't that, am I going to be able to travel back in time with this? It's like, no, right? What a capacitor does is actually it stores charges, okay? So that's actually a very useful thing. You can imagine in your device, if you want to store some charge in your device, you know, you want to keep that energy, right? You want to set up a certain potential, you want to set up a certain electric field. You can see how this is useful, right? So what we're going to do is kind of think about the simplest version of a capacitor, which is just 2 parallel plates next to each other, okay? Right? We're going to make it so that, you know, maybe we'll have some positive charge here, right, and some negative charge here. Remember we talked about the battery. You know, let's say you hook this up to a battery, right? This will allow you to set up this little situation, right? Okay. So remember, then in a parallel plate situation, right, the electric field is constant, right? In fact, the magnitude of that electric field is just the charge density divided by epsilon naught, right? So what you can do is that, while using that, if you want to figure out the voltage across a constant electric field, right, you can actually pull this out of the integral, right? It's just E dot ds, right? And therefore, right, this dot product, if the displacement and the electric field is in the same direction, right, this just turns into the magnitude of the electric field times delta S, and if delta S is just kind of like equal to negative S, then you just got E times S, right? That's the voltage across a parallel plate capacitor like this, okay? So you can start, you know, fiddling around with the algebra a little bit, right? So we figure out what E is. E is the charge density divided by epsilon naught, right? So, but charge density, right, is how much charge there is per area, right? Right. So we can put Q, which is the total amount of charge on one of the plates. This is Q on, let's say over here, on one plate. Okay. Divided by the area of that plate, right? So this plate is actually a 2-dimensional thing, right? So there's some area to it, right? I just don't draw it usually. All right, so that's kind of an interesting thing, right? I'm going to just fiddle around a little bit more with the algebra. I'm going to just factor out this Q in front. And now I have a relationship where the voltage across some parallel plate thing is equal to the charge times some factor. And this factor happens to be S, which is the distance across the plate, the area of the plate, and then this epsilon naught constant, right? That's just a number that we can look up, okay? And this little factor here, okay, we're going to call that the capacitance, okay? Okay? And therefore, if we just replace this whole thing with this number called capacitance, right? Right? Therefore, and we're going to call that, use the letter capital C. I'm going to try to make it big to represent that. Okay? And therefore, the charge across a, oops, I did the upside down thing. Okay? So what I'm going to do, I'm going to do one more trick, okay? Where I'm going to solve this equation here for charge first, okay? I'm going to solve this equation for charge, and therefore it's delta V, okay? But then instead of this, when I solve this for charge, right, this goes in the numerator, this goes in the denominator, so this is actually area epsilon naught divided by S, okay? What I'm going to do is I'm going to call this entire factor C, okay? The reason I can do that is because, right, the area of a capacitor, once you pick your capacitor plate, the area stays the same, right? It doesn't change, right? The spacing between the capacitor also doesn't change once you set up your system. Of course, epsilon naught is just the permittivity of free space. Therefore, it's just a constant. And we're going to call this just the capacitance of an object. And this object we're going to call a capacitor. Capacitor, right, is the parallel plate itself. The capacitance is how big or small that capacitor is, okay? And we're going to see some examples of this today, okay? Some neat things about this unit of capacitance, okay? So area, right, has units of meters square. I'm just going to highlight so I don't overwrite things, right? Epsilon naught has units of newtons meter square coulomb square, right? This crazy constant that we have to deal with all the time. Well, of course, the distance s has units of just meters, okay? If you simplify all of this, what it turns out to be is going to be coulomb square per joule, okay? And there's a reason why I split up the two C's, right, instead of saying coulomb squares, right? And be careful, right? The variable capacitance is represented by capital C. The unit coulomb is also represented by capital C, okay? So just be careful about this, okay? So you have to know which, am I dealing with the units or am I dealing with the variable C, okay? The physical representation of that, okay? So a joule per coulomb, okay? Why is that special, okay? So what is a joule per coulomb? What has units of joule per coulomb, okay? Right, remember, joule is a unit for energy, right? So in this case, some sort of electrical energy, right? Coulomb is a unit for charge, right? What quantity has unit? What will be a energy per charge? What physical representation is that? Was that? Well, the unit is voltage, but then yes, technically called a electric potential, right? Yeah, but voltage is correct, okay? So this is going to have units of whatever volt has, right, which is a volt, okay? So actually a capacitance has units of coulombs per volt, okay? And the nice thing about this is, think about a capacitor is that the bigger the capacity, the more charge it can store per volt, right? If you have 1 volt, the bigger the capacitor, the more charge you can store, right? The smaller capacitance, the smaller amount of charge you can store, okay? And this is a nice way to think about it, right? Bigger the capacitor, the more charge you can store with the same voltage across them, okay? And of course, you know, as usual, people really like to name things after themselves, and the unit for capacitance is actually named after microfaraday, or known as a farad, and the units we use, the shorthand for that is just F, okay? Okay, it's not as useful, but that's the units that everyone uses, okay? Okay, and this capacitor comes in different capacitance, different sizes and shape. Most electronics will have capacitance of somewhere on the order of a micro, a nano, or a picofarad, okay? Anything that goes in your devices will have these type of capacitance, okay? usually capacitors are very small, okay? Okay. And the reason for that is because 1 coulomb of charge is actually a lot of charge, okay? So, you know, these are various different types of capacitors. So there's this little cylindrical type, there's this little block type that you see, and there's these little ceramic plates that you can see. And we're going to play around. Well, if we have time today, we'll play around with them, but if not, that's okay. Okay? Because a 1 farad capacitor is actually huge. Okay? This is a 1 farad capacitor. So you can see the hand size here, right? So it's going to be something like this big. Okay? Right? It's like a gallon of milk or something like that. Okay? That's a 1 farad capacitor, because remember, this tells you if the capacitance is 1 farad. Okay? It tells you that it stores 1 coulomb of charge if you apply 1 volt potential across it. By just applying 1 volt across it, you can store 1 coulomb of charge. Okay? What I'm going to do is going to play around with this little exercise. Okay? So this thing, right, is designed to have 1 farad of capacitance. And the way they make these is by basically, like, if you ever seen it's basically like kind of like a double sheet of toilet paper, where if you have the top-down view on this, right, looking straight down on it, what they do is they basically have these parallel plates. I'm going to do the other ones. And they roll it up, you know, basically like a 2-ply toilet paper situation, right? And that way you increase the area between the plates. So I increase the area of the plate themselves without making a giant device, right? Because imagine if you take a roll of toilet paper and just spread it out all over campus, right? You're going to have a lot of toilet paper that you're going to have a large area just with a single roll of toilet paper, right? So that's probably a better demo today, right? Just bring some toilet papers in here and make a big mess, right? So can you see how, do you guys see how this capacitor can have a large area by rolling all these little layers of capacitor plates up, right? But still kind of fitting it in, you know, it's pretty big. It's like this big, but that's 1 farad, okay? And I want you guys to think about is that, well, let's say instead of this fancy parallel plate, right, let's say I'm just going to make 1 plate next to each other. I want to make the same 1 farad capacitor, okay? And then the separation distance between them is 1 centimeter, okay? You know, just a little bit, okay? If you have a calculator, right, can you guys calculate what would be the size, what would be the area of this little parallel plate? Anyone have, if you have a calculator with you? Okay. What do you think it's going to be, actually? If you don't have a calculator, just estimate, is it going to be like, you know, a centimeter square, a meter square, a kilometer square, right? 100 kilometers square or 1,000 kilometers square, okay? What's the area, do you think, okay? If you have a calculator, you can calculate what this is. So I'm going to do that. 1 times 0.02 divided by, because basically you're solving this equation for A, right? This will be C times D divided by epsilon naught. 8.85 e to negative 12. Okay. Those of you with a calculator, anyone want to volunteer what they figure out the area has to be? What's the number you guys see on the calculator when you punch this in? 8.85 times 10 to the negative 12. Okay, I can see. What's the number you got, Matthew? Just the 1 sig fig. You don't have to, like, 1 times 10 to the 9. Okay, this will be in meters square, right? Because that's the SI units, right? If you want to convert from meters square to kilometers, right? 1 kilometer is 1,000 meters, right? But you need 2 factors of them, so you have to square both, right? You multiply this out, right? This is actually 1,000 square kilometers, right? So 1,000 square kilometer is probably, it's basically like, you know, like Turlock, you know, Ceres, Modesto, kind of all combined together, okay? So for you to make a 1 farad capacitor, with a separation distance of 1 centimeters between them, you have to basically cover like most of the Stanislaus County in order to do that, okay? So that's why we don't do that. That's why we roll up these toilet papers, okay? So anyway, so when you have a capacitor, what you can do is, well, the reason for capacitor is that you can store charges on it, right? And the way you store charges on them is by using this thing we learned last time called battery, right? A battery, right? The idea of a battery is that you take some positive charge on the negative end, it basically increases the potential energy of that charge, and then it comes out on the positive end, okay? Right? A battery provides potential energy, right? Because this will give you some change in potential across that battery, okay? So if you connect the positive end to the positive end of your capacitor, the negative end to the negative end of the capacitor, what will happen is that these positive charges will start piling up on the positive end of the capacitor, okay? What will happen is that these positive charge will actually attract negative charge to the negative plate, right? Because here you have a electric field between them, and this electric field actually goes through here, right? If you have an electric field, right, the electron's gonna go backward along the electric field, right? So these little electrons are attracted and goes up. Let me do a different color there. Right? You have a little bit of electrons. Change the color. I think I'm just moving too fast for the computer. Right? Right? This will get attracted to the plate and kind of distribute it along the plate. Okay? So what ends up happening, and this usually happens on the order of like a microsecond, right? Once you hook a battery up to a capacitor, right? This, right? The positive plate will build up enough charge so that whatever the potential difference between the capacitor plate is going to be equal to the battery. Okay? Right? Because when it's equal, then they're kind of offsetting each other, and therefore, now as you go around this loop, right, the change in potential is going to be 0. Okay? Right. So let's see what happens if we do a more complicated thing called either parallel or series capacitor. Have you guys dealt with either parallel or series circuits in your labs yet? Okay, we'll play around with that today, right? So instead of just one capacitor, right, with some capacitance C, let's say I hook a battery up to 3 different capacitors, okay? Is there a way for us to figure out how much charge or what is the equivalent capacitance to this, okay? Right? So if we declare that the negative end of the terminal here as being 0 volts, remember, just like potential energy, right? You can declare one point on your circuit to be 0. Once you pick that point, everything's relative to that, right? Okay? So therefore, right, the positive terminal is going to have some change in potential, right? We're just going to call that this squiggly E, which stands for the EMF, the electromotive force, right? What units does electromotive force have? Is it a Newton or is it something else? It's a what? It's volts. Why is it a volt? It's a force, right? No, it's not a force. That's the crazy thing, right? So the electromotive force is a voltage, so therefore it has units of volts. And as I said yesterday, instead of electromotive force, you can say in electromotive, voltage or something like that. Okay? Think about it as that. Okay? So therefore, right, when you hook this little battery up to it, all 3 capacitors, so unfortunately this is just a bad typing, right? The equation for that governs how a capacitor behaves is that the charge is equal to the change in voltage across that capacitor times the capacitance, right? So therefore, I know that, well, after you hook up the battery for more than a microsecond, the change in potential here across here is going to be EMF. The change in potential across here is going to be EMF. The change in potential here is going to be whatever the EMF of the battery is, right? If it's 1.5 volts for the battery, right? There's going to be 1.5 volts here, 1.5 volts here, 1.5 volts here, right? Make sense? Because it's just connected directly through a wire, okay? All right, so the total amount of charge here, right? So we have this equation, right? If we know the voltage across the capacitor, and we just multiply by the capacitance, we figure out how much charge is on each of the capacitor, right? Right? Therefore, the total amount of charge across all three capacitors combined, right, is just charge 1, charge 2, charge 3, right? Hopefully that makes sense, right? You have 10 coulombs, 20 coulombs, 30 coulombs. You add them all up, you get 60, right? Okay. But, right, since we have all these relationships, right, we can replace all of this with our EMF times C1, EMF times C2, EMF times C3, right? Since the EMF is the same, just doing a little algebra, we can factor out the EMF, right? If we factor out the EMF, we end up with C1 plus C2 plus C3. So therefore, right, if we have a battery with 3 capacitors, 2, 3, right, C1, C2, C3, is equivalent to having a battery and a single giant capacitor, a bigger capacitor. I'm going to call that CEQ, EQ for equivalent. And that equivalent capacitance is just going to be C1 plus C2 plus C3, right? Because that's the same thing, right? That's exactly what we have here. Does that make sense? No? Yeah, Cole?
Is the area of that larger capacitor the area of that EMF?
Well, it's the equivalent capacitor is not a real capacitor, right? What we did is we just imagine that, oh, well, if I have 3 different capacitors on this circuit, okay, what will be the equivalent of that if I want to combine all 3 of them together? Okay, this is not a physical capacitor. This is like an imaginary one, okay, where, oh, this is the equivalent of adding all three things together, okay? That was a good example of that. It is interesting what you mentioned. The area of the capacitor should be, if you have a bigger capacitor, right? Because the capacitance of it, the capacitance of capacitor, right, is area divided by the distance between them divided by epsilon naught, right? Or is it multiplied by epsilon naught? Maybe it's multiply. I'll put that epsilon naught in the right place. But it's proportional to the area, right? So you are kind of thinking about this the right way, where if you have these parallel capacitors, just imagine that, you know, kind of these area kind of adds up, right? And you get a bigger capacitor, right? Right? So when you have capacitors in parallel to each other, right, it just makes a bigger capacitor. So therefore, the general way to calculate this equivalent capacitance is just that, oh, well, if you have capacitors in parallel, you can just add the capacitor values up, okay? So if this was 1 microfarad, right, this is 2 microfarad, and this is 3 microfarad, right, the equivalent will be 6 total, okay? And this may seem very obvious, right, but we're going to see another case right now, right, that is not going, we're not going to be able to add these capacitor values up just by just adding the numbers together, okay? Because I'm going to do is I'm going to throw you guys a little trick. Instead of hooking the capacitors up in parallel to each other, I'm going to connect one after the other. This is known as a series, okay? So it's one after another, okay? So in this case, right, if I was to try to figure out the equivalent of this will be, right, let me just draw this battery here. Just imagine there's a battery here, okay? Okay. What will be the equivalent capacitance here, right, if I try to combine these 2 capacitors together, okay? What would that be, okay? Is it just going to be C1 plus C2, right? So let's see what happens, okay? So remember the rule is that the change in voltage across a capacitor, right, is going to be the charge times the change in voltage across that particular capacitor times the capacitance, right, But since these things are in series, right, we're going to have to figure out, well, there's going to be some charge 1, change in voltage 1, capacitor 1. There's going to be some charge 2, change in voltage 2 times capacitors 2, right? Okay. The problem is that the change in voltage here, right? Let's say this is like a 9-volt battery, right? Is the change in voltage across capacitor 1, is that going to be 9 volt? No, because there's another capacitor you have to go through, right? So there's some division about the change in voltage between capacitor 1 and capacitor 2, right? Right. So what it actually is, right? So this is called the EMF. The EMF is going to give you the change in voltage across capacitor 1 plus the change in voltage across capacitor 2, if I can write 2, right? Right? Because when you get across capacitor 2, that's when you get to the negative end of the battery, right? Okay? Right. Therefore, right, in order for me to solve this, right, I have to solve this equation for delta V's, right? So delta V1 is going to be Q1 over C1. Delta V2 is going to be Q2 over C2. Okay? So we're going to replace that. Oops. I'm going to replace it. Go up. Right? Q1 C1 plus Q2 C2. Okay? That's the EMF, right? Okay? So the one thing that's interesting is that if you were to start, remember the idea of capacitor is to store positive charge on this end and negative charge on the other end, right? If there are, let's say if there's 1 microcoulomb of charge here, right, those negative charge, right, has to come from somewhere on this wire, right? Okay? In fact, it comes from the other plate, right? If there's 1 microcoulomb of charge there, it's going to create 1 microcoulombs of charge, positive 1 microcoulombs of charge here. So this is the negative. This gives you the positive. Does that make sense? Where remember, before you connect the battery, this has no, I mean, the net charge of that is 0, right? If I pull 1 microcoulomb of charge up here, what's left over is 1 microcoulomb of positive charge, right? Because the charge has to add up to 0 on that part of the circuit. Okay. Therefore, right, this is the bottom of this plate, right, will also have negative 1 microcoulombs of charge. Sorry for the messing up the negative signs. Right, this is actually positive here, right? It's positive 1. So what's interesting about capacitors in series is that it's actually the charge, the amount of charge on them that are the same, right? So I can use that, right? Because over here, I have 2 different charges, right? Q1 has to be equal to Q2, has to be equal to, I'm just going to call it Q, right? So therefore, I can actually factor out these Q's, right? Therefore, 1 equal to 1 over C1 plus 1 over C2, okay? Right? And remember, the main thing you want to remember about capacitor is that the charge is going to be equal to whatever the voltage is times the capacitance, right? So if I solve this equation for charge, let's go to green here, right? This is going to be whatever the EMF is times 1 over C1 plus 1 over C2 to the negative 1 power. Okay? So this is the equivalent capacitance when you combine 2 different capacitors together. Does that make sense? Okay? So in general, right, capacitors in series acts in reciprocal. Okay, this is what you want to kind of remember in the back of your head. Okay, if the capacitors are in series, it's going to be in the reciprocal. Okay, adding reciprocal means you take the reciprocal of the capacitance, you add them together, all 3 of them, and then you take the reciprocal of the whole thing. Okay, So my way to remember capacitance is that it's just, I think that what Cole intuition tells you is that when you have capacitors in parallel, you can just kind of think of, oh, it's just making a capacitor that has a bigger area, right? Okay. And when you're just making the capacitor with bigger area, that means you're increasing the capacitance, so you can just add C1 plus C2 plus C3 and so on, okay? Okay, this is parallel, okay? When you have capacitors in series, when you have capacitors in series, it's the charge on each of the capacitors that are the same, not the voltage, okay? When you have that, right, then they're going to add in reciprocal. Reciprocal. Is that how you spell that? And this is where I always call this the more complicated equation, the harder equation, right? Because I know how to add C1, C2, C3. That's very easy to do, right? But when they're in series, it's the harder equation, right? This is where you have this reciprocal of a reciprocal situation. Okay? So let's do a solid example here. Let's say I have this kind of complicated circuit, right, where I have 1, 2, 3, 4, 5 different capacitors, okay? What will be the equivalent capacitance of this entire trees of series and parallel capacitors together? This is called a system of capacitors, okay? Okay. So the way you diagnose this is by kind of staring at it for like maybe a minute, right? And then you try to figure out, is there any point that I can simplify this circuit right away, okay? Okay, and the book example kind of pointed this out to you. But, right, you can see here that, well, if I want to figure out what is the capacitance of all 5 of these things, right, I want to figure out where there's a subset that simplifies very easily first, okay? Right? The problem is that I cannot add this one and these the 2 together because they are parallel and series at the same time, right? So what you want to figure out is a way to find a particular spot where they are only series or only parallel, okay? So in this part of the circuit, right, it's only series, okay? So this is only series. So what I can do is I'm going to make a first attempt at the equivalent first. We're from point A to point B, right? I'm going to combine those 2 capacitors together first, okay? Right, because I know how to add capacitors in series, okay? So this is whatever C equivalent, I'm going to call that A, right, because we're going to have to do this multiple times, okay? So C equivalent A, right, it's going to be the complicated formula, right, because series are the complicated ones. 1 over C1 is just going to be 2 microfarad. C2 is 6 microfarad, okay, all to the -1, okay? And there's a trick to this, instead of dealing with all these microfarad stuff, okay, what I'm going to do is I'm going to just compute this as 1 over 12 plus 1 over 6, take the reciprocal of it, and then the microfarad units actually just stays, okay? 1 divided by 12 plus 1 divided by 6, right, to the -1 power, okay? This would be an equivalent of 4, right? I'm just completely ignoring these units, right, for now, okay? Because this is in the denominator, right? When you reciprocal something, you put that in the denominator also, right? So this unit is actually in the denominator of a denominator. What does it make it? Where should I put it? In the numerator, right? So I can just basically put this in the numerator. Okay. So the equivalent of 12 microfarad in series with 6 microfarad is actually only 4. When you put capacitors in series, it actually decreases their value. Okay? So that's what this is. Okay? Now, right, what I'm going to do next is I'm going to combine all three of these together. Right? Because now I see that, well, this is parallel, 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 right? These three capacitors are all in parallel to each other. So what I'm going to do next is I'm going to make the equivalent, right? Let's go down. I'm going to combine all three of these. So how many capacitors will I have left now if I combine those three together? Two, right? Okay. A, B. Okay, so I'm going to call this C equivalent B, right? This one down here is still 9 microfarad, right? That one corresponds to here, right? This one corresponds to all three of these, right? Well, these are in parallel to each other, right? I know how to add capacitors in parallel. C equivalent B is just going to be C1. C1 is 3 microfarad, right? C2 is 11 microfarad. C3 is what? Is it 12 or 6?
4.
It's actually 4, right? Because we did the equivalent thing. We want to actually add the equivalent. Okay, so that turns out to be 18 microfarad, right? So that's what C equivalent is. Okay, one more step, right? To get the total equivalent, right? We're going to combine both of these into the answer, which is without the letter, right? A and B. How are these capacitor arranged now? Are they in series or parallel? In series, okay? So I have to use the more complicated formula. Okay? It's 1 over CQB plus 1 over, well, 9 microfarad. Okay? And CQB was 18, so, oops. So 1 over 18 microfarad plus 1 over 9 microfarad, all to the negative 1 power. Okay? So 1 divided by 18 plus 1 divided by 9, all to the negative 1 power. You get 6. And remember, this is in the denominator of a denominator, so it actually flips up to the numerator. Okay? So you get 6 microfarad. Okay? So that's the answer to this complicated, instead of dealing with 6 different capacitors, it's equivalent to just 1 of 6. And it's a weird combination, but okay. There are other examples in the textbook, right? I'll let you guys work through those. Okay. Yeah, question, Alan?
The capacitor, what is in between the phase? Is it a vacuum or a
Yeah, that's actually the section 7 of this chapter. Right now we're calculating it as if it's vacuum, okay? But air is pretty close to vacuum, actually, okay? But we're going to see if we insert different things in there, it's going to give us a different capacitance, okay? So before we can talk about the stuff that we're going to put between the capacitor, we have to talk about what is the energy that is stored in between these capacitors, right? Remember when you put charges next to each other, you're storing energy, right? So let's start off with the fact that, well, the change in voltage across anything, right, is just the electric potential energy divided by how much charge you have, right? Right? U over Q tells you what is the voltage. Okay? So in this case, right, the change in voltage across a capacitor when a bunch of when a battery start moving charge from the battery over to the positive plate. Let's say we're going to add, every time the battery does this, it puts a little bit of tiny amount of charge dq. This is a differential of charge, okay? You could have used delta q, but I think the book just want to skip right to the calculus, okay? Therefore, the amount of energy, okay, that is used to do that is basically how much the voltage across, the voltage across this capacitor, as a function of time. And what we're going to do is that if you have a constant, this is a constant voltage, and delta V lowercase is going to be a time-dependent voltage. Okay, we're going to start using this technique where if it's capitalized, then it's a constant. If it's lowercase, it could be a variable. Okay, even though it doesn't write it. Okay, right? Because what's happening is that as you move these charges here, you're building up more and more and more voltage across this capacitor, right? Okay, because you're increasing the charge density, right, as a function of time. Okay, so therefore, right, the amount of potential energy you store into the capacitor is a little bit of voltage that changes with time, times how much charge you put on there. Okay, so therefore, the infinitesimal amount of energy that you place onto the capacitor is actually the change in voltage. That's a function of time, depends on time, times the amount of charge that you're putting on there. Okay, but remember, no matter what, okay, the capacitor equation is always obey, because we defined it this way, right? The amount of charge on the capacitor is the voltage times the capacitance. Okay, this also happens if you have the time-dependent case, right? Delta V, that depends on time. Can the capacitor depend on time? It depends on what? The area and the separation distance, right? So it cannot depend on time, right? It has to be a constant. Okay, so instead of writing this delta V, we're going to solve this for delta lowercase v, right? This is going to be Q as a function of time divided by the capacitance, right? That's what we're going to replace with here, okay? Right, see that? So now, right, we have this kind of fancy equation, du equals to Q, which depends on time, right, divided by C dq, okay? Right? The right-hand side here, right, is if I integrate the left-hand side and the right-hand side, okay, what happens is that the left-hand side just becomes delta U, right? It's just like integrating dx, right? That just becomes delta x, right? Okay. The right-hand side, right, is Q times dq, right? So the integral of that should be what? Q to what power? Right, Q squared, exactly. Sorry, I'm just going to move stuff around so it's easier for me to write. Okay, this becomes Q squared, right, over C, evaluated from initially the capacitor had no charge. The final amount of charge is this constant at the end, right? So therefore, the amount of energy stored in capacitor is actually the amount of charge on its square divided by the capacitance. Okay. Oh, yeah, 2. Good catch. I always miss that 2. I did that yesterday too, didn't I? Yeah, some bad integration, right? It has been like 21 years since I took a calculus class, right? I have an excuse. What's yours? Okay, so that's the energy stored in the capacitor, right? Q squared over 2C, or you can rewrite this by just taking the equation for, Q is equal to delta V times C. You can do a substitution in here, and you can actually calculate that. The energy stored in a capacitor is 1/2 the capacitance times the voltage squared. Okay? Does this equation remind you of anything that we've seen before that's not about electricity and magnetism? I'm sorry? Motion? 1/2 mv squared. Yeah, kinetic energy is 1/2 mv squared. Right? Okay? The energy stored in a spring is 1/2 kx squared. Remember that? You notice that all these energy always is like 1/2 times some constant times your variable square. Okay? It's always neat that way. Right? So let me just take this minute to wrap up here. Right? So one more thing we can do is we can actually convert this voltage into electric field, or at least just the magnitude of electric field, right? Right? Because the voltage across any parallel plate, it doesn't have to be a capacitor, right? It's just the electric field times the separation distance between them, right? And that's this little drawing showing you. The electric field is just the voltage divided by, okay, I'm going to use S instead. Okay. I don't know what the book you actually uses D. All right, so the book decided to change the variable that it's using. So instead of S, it's D. So let's just stick with D since the book is doing that. Okay. So what we can do is we can massage that equation we just derived up top, right? This 1/2 times the capacitor delta V squared, right? Instead of writing delta V, what I can do is write E times D, right? Because that's the same thing as, oops, I don't know why they did this. Okay, the voltage across here is just the electric field times the distance between them. Okay, right, and that all of that gets squared. And instead of writing capacitance, right? Remember, capacitance is the area of that particular plate divided by the separation distance between them times epsilon naught. Okay, so that's what this one does. That gets you this step. Okay. Now you do a little massaging and factor out the E square, right? You will find that the amount of energy stored in a capacitor is proportional to the electric field square. Okay, that's sort of the important point. Okay. Okay. So the bigger the electric field, right, it gets squared. That's the amount of energy that you get. Okay. Okay, energy is basically proportional to the electric field strength square. Okay, and that's the point I want to get across before we wrap up today. So unfortunately, we don't have time to do the worksheet today. I'll steal a little bit of time for Monday to work through this little equivalent capacitor exercise.